Internet. This is Taylor Feldman with Mount St. Helens Institute coming to you live for our virtual Views and Brews for November. Tonight's presentation, oops, I am getting feedback. There we go. Always some technical difficulties. You'd think by month 8 we'd get it, but maybe month 9 is our time. All right, so Mount St. Helens Institute, we are a nonprofit partner to the Forest Service. We've been around since 1996, and we are proud to advance understanding and stewardship of the earth through science, education, and exploration of volcanic landscapes. And now we have the opportunity to do so virtually. We believe in the power of science to help lead us down the right path, solve problems, inspire critical thinking, and make the world a better place. We believe the natural world around us is an irreplaceable resource to be respected, to be loved, understood, and cared for. And we as an organization are committed to diversity, equity, and inclusion throughout our organization's cultural policies, curriculum, programs, and partnerships. And we believe everyone should have the opportunity to enjoy Mount St. Helens. We always have, and we always will. No matter where you're joining in from, we encourage you to recognize and learn about the indigenous cultures and land on which you live. Here at Mount St. Helens, we operate on the land of the Cowlitz tribe and the Confederated Bands and Tribes of the Yakima Nation. We're honored to have the Cowlitz Indian tribe as a partner, where they fill multiple seats on our board of directors, and together we can offer joint programming to Cowlitz youth and to the general public. If you enjoy Views and Brews, consider making a donation. We're gonna go ahead and put a link to donate into the live stream chat and description here on Facebook. It'll take you to our donation page. We really, really appreciate any support that you can offer us during this time. We know times are tight for everybody. We'll be collecting questions via our Facebook chat on this live stream. So if you have a question as it comes up, feel free to send a message to the speaker. I'll collect them and then I'll answer them all at the end. So cheers to all of you who are out there joining us tonight. Whatever your brew is, I have kombucha from Oregonic Tonic, Portland brand, and cheers to you. So tonight we present community snow observations, how backcountry users can better build snowpack models with Professor of Water Resources from Oregon State University, David Foster Hill. David is also an explorer with the National Geographic Society. So welcome, David. Thanks for being here.
Great, thanks so much. Give me a second and I will share my screen.
I'll just go ahead and take a sip of my brew.
Okay, if I did that right, you guys are seeing my title screen here. So yes, thanks. Good evening. Welcome to Views and Brews. I'm super happy to be here. To talk to you about snow, water, citizen science. I'd like to thank Mount St. Helens Institute for the opportunity to do so. And thank you for spending part of your evening with us.
And David, I'm just going to pause you for just a moment because we are seeing your whole screen, including all of your notes. So
oh, weird.
I wanted to
I think I need to share my other monitor then.
Let's try it again.
Let's try this again. Desktop 1.
There we go.
So you're seeing a full slide now?
Yes.
Okay.
All good now.
Awesome. Let me see if this will work then. Sorry, I thought we had this all worked out last time. Okay, so good. Anyway, expectations for tonight, very important. I assume that we've got some people online who are into science. Okay, that's fantastic. The diameter of this purple circle, okay, this might represent the percentage of you who are interested in science. Okay, we've also probably got some people online that are into beer or mead. Jared, that's okay too. We are inclusive. That's shown by the diameter of the blue circle here. So where are we going? Well, this is where we are right now. All right, we've got some people that are liking beer, some people that are liking science, and some that are liking both. Okay, so that's great. This is one possible outcome of the evening. All right, if after an hour I've got some more people interested in science, that's fantastic, and I would sign off happy. This is also a possible outcome of the evening, I suppose. I don't get anybody more interested in science, but some of you leave with a greater interest in beer or mead. That's also good. Okay, so it's in the title of the lecture series after all, Views and Brews. don't be this people, okay? This will disappoint me if I turn you off of both science and beer in one fell swoop. So I hope that this is not where we end up tonight. This is where I would love us to end up tonight, okay? So I hope that you have a favorite brew in hand, all right? And that you leave here with a greater appreciation of both snow and water and science. All right, so let's get started. Kind of at the core here, this is really a talk about hydrology. Okay, so more specifically, this is a talk about the landscape portion of the hydrologic cycle. Essentially, we have weather, and we add to this a landscape, and our landscape takes this weather, and it turns it into a time-varying signal of something of interest to us. So I've shown snow depth here on the vertical axis. I could replace that with stream flow, for example. So there's many different variables that interest us. So that right there is basically the elevator speech version of hydrology. Our landscape transform weather inputs into snow or water outputs. We can also think about hydrology in terms of a sort of a simple box model. All right, so we have some domain of interest, usually a particular watershed, or let's say a local catchment. The Columbia River Basin is a good example. It's a very large scale example. And now we have a number of fluxes, okay, of water into our watershed. Precipitation is a great example. It's the major dominant flux into a watershed. We can also have a number of fluxes out of our watershed, including evaporation, river flow, groundwater infiltration. These are all pathways for water to get out of our watershed. Now, if the stuff coming in doesn't balance the stuff going out, then we have either the gain or the loss of water, which is called storage in our watershed. So again, hydrology, it's simple. It's just a bank account. You've got deposits, you've got withdrawals, and you have a fluctuating balance, okay? So let's talk for a few minutes about precipitation, since it is our major input of water. Okay, so here's a map of global precipitation for August 2006. And as you can see, different parts of the globe get radically different amounts of precipitation. The Pacific Northwest is very dry at this time, as is Australia, Southern Africa, Northern Africa, and the Middle East. Okay, at this time of the year, on the other hand, Southeast Asia and India are experiencing their extreme seasonal monsoons. Now, if we switch to December of 2006, you'll notice that the Pacific Northwest, very rainy at this time, of course. We have large rains in Southern Africa, but we have now very dry conditions over much of Asia. So there's extreme seasonality in precipitation inputs over much of the globe. The global average for annual rainfall is about 1 meter. Okay, but much of the heavy rain is over the oceans, especially, you can see it in this picture, the equatorial regions. If we restrict ourselves to just land surfaces, then the average rainfall is about 800 millimeters in 1 year, a little bit less than a meter. Now, if we zoom in a little bit and turn our attention to the Pacific Northwest, there's definitely a lot going on. Okay, so we see significant differences between the western 1/3 and the eastern 2/3 of both Washington and Oregon, right? And this is due to what are called orographic effects. And what this means is that we have lifting of easterly traveling moist air by the Coast Range and the Cascade Ranges, and this promotes rainfall. So storm systems that actually make it to central and eastern Oregon and Washington really have very little moisture left over to drop. Now, averaged over the state of Oregon, the annual precipitation is about 700 millimeters. It's about 1,000 millimeters in Washington. Now, if you combine this precipitation depth with the area of either Washington or Oregon, it works out to about a precipitation volume of about, if I did my math right here, my beer math, 300 trillion pints of Pacific Northwest craft beer, okay, for either state. So we're talking about a lot of liquid. Now, I'm more interested in snow, all right? And so just because something's wet doesn't necessarily make it white. Winter temperatures vary a lot in the Pacific Northwest, mostly demonstrating changes with distance from the coast. So another way of thinking about this is that we have a maritime climate close to the coast where things are warm and they don't change that much from season to season. And then we have a more continental climate farther from the coast where we have significant differences in temperature between winter and summertime. So if you take some wet, if you add some cold, this is of course what you get, all right? So we get the snow that we're looking for. Now in Oregon, the snow is mostly confined to the Cascades and to the Wallowas. In Washington, there is a larger footprint that includes the Olympic Peninsula in addition to the Cascades. So one thing to note about this particular figure, the depth amounts that are being shown on this figure are the water equivalent of the precipitation that falls as snow, okay, not just the depth of snow. And for Oregon and Washington both, it turns out that about 15% of our annual precipitation falls as snow. Okay, so there's admittedly a great deal of variability in snow from year to year. All right, we've been talking about just kind of averages so far. So in this case, near Mount Rainier in 2011, we have an incredible snowpack. At the other extreme, in California, in this particular year, we see exactly 0 snowpack. So if you've kind of forgotten the winter of 2015 for Washington, Oregon, and California, it was a pretty dismal year. And especially so in California, where basically the snow just did not show up. So this picture is from Echo Summit, and it's on April 1st, 2015, with then Governor Jerry Brown in the center. Now, April 1st is historically the day of peak snowpack in many areas. So snow surveys are conducted on that day, are kind of good indicators of how much spring runoff there will be for irrigation, other purposes. So in a typical year at this location, there might be multiple meters of snow. In this year, 2015, though, there was exactly 0. So we have a lot of variability. Sometimes we have a little, sometimes we have a lot, but the distribution is always complicated. So in this animation, which spans a single water year, we see the gradual buildup of snow in high elevation mountain regions as winter progresses. However, we also see these large swaths of snow that are created in lower elevation regions across the central and the northeastern US. And this is due to these large winter storms that move across the country. And then eventually in late spring, we see the steady retreat of the snowpack northward. And something else to sort of be aware of is that the future of the Pacific Northwest is predicted to be wetter and warmer. Now, the wetter part sounds great for snowpack, and there will be significant increases in precipitation many decades out, but the warmer part is not great. So these particular figures that I'm showing you here are showing late 21st century snow precipitation changes. Okay, and this is for a sort of pessimistic scenario. It's the RCP 8.5 scenario. And basically everything in this figure is yellow, orange, and red. So we're losing snow everywhere. Nowhere in the Pacific Northwest are there going to be gains in snow. Okay, so we live in a place with snow. Why does it matter? Well, there are many reasons. First of all, snow is big business. Okay, a 2018 study of winter snow sports industries found that in the USA, over 50 million skiing and snowboarding days and 11 million snowmobiling days added then more than $11 billion to the US economy in a single year. Another reason that snow matters is that it acts as a natural reservoir. So when precipitation falls as snow, it doesn't run off right away into our rivers. It may stay in place for several months before eventually melting and then running off in the spring. So by impounding water and holding it back for some amount of time, the snowpack reduces peak river flows, and this helps to reduce flooding hazards. So the advantage of the snow reservoir is that it's very low impact in the sense that it leaves no permanent imprint on the landscape, right? And it doesn't interrupt freely flowing rivers. A third reason why we care about snowpack is that it provides habitat for a great number of species, right? Spring snowmelt does a lot to help keep river volumes high and to keep the stream temperatures cool. And this is good spawning habitat for many fish species. Other animals, such as wolverines, depend directly on the snowpack itself, and not its runoff. So they utilize the snowpack for caching food, denning, and other types of activities. Okay, so snow is important to us for a bunch of reasons. It would be great, therefore, to sort of learn about it. How much of it is there, and where is it, and when is it? These kinds of things. So an easy way for us to learn about it is to simply go out and measure it. And there are many ways of doing this, all right? So two of the simplest snowpack properties to measure are its depth and its weight. Okay, the depth, that's the easiest. Okay, you can measure this in a bunch of ways. All you need to do is take a ruler, take a tape measure, take anything like that, stick it into the snowpack down to the ground, and you're done. There are also indirect or remotely sensed ways of measuring the snow depth. And these can be made from fixed platforms like an instrument tower, or they can be made from mobile platforms like a plane or a drone, or frankly, even a satellite. So the distance between the measurement platform and the bare ground is going to be a known quantity, either based on direct measurement or accurate GPS devices and so forth. Now, the distance between the platform and the snow surface is then measured, right? How do we do this? We do it by timing how long it takes a signal, either a sound wave or laser light, to bounce off of the snow surface and then return back up to the instrument. And if you know the purple length and if you know the red length, then simple subtraction ends up giving you the depth of the snowpack. Now, for a fixed platform, these measurements can be made repeatedly, and you can create a time series of how the snow is changing over days or months. Now, for a moving platform, due to the motion of the platform, repeated measurements end up giving you this two-dimensional map of snow depth, essentially at a single time. So a plane might fly back and forth for a few hours and collect information like you see here. So this is showing you a map of snow depths in the maroon belts in Colorado. Now, due to the expense of airborne surveys, these types of maps might only be produced like once a season or once a month, something like that. So you can't be doing these types of things on a daily basis. Now, measuring the weight of the snowpack is a bit more complicated, and it requires a bit more specialized equipment. And one way of doing it is to use a snow coring device to essentially extract a column of snow, and then you end up weighing that. And just basically knowing the length and knowing the weight, you can figure out the density, these kinds of things. So manually weighing the snowpack is fine. It does take some time and effort. Okay, so this is not a super quick measurement. To automate this process, snow pillows were invented. All right, now if you're a skier or if you're a split boarder, you're probably pretty psyched that we're going to talk about snow pillows. But these are not the types of snow pillows that I'm planning on talking about tonight. These are the snow pillows that I'm more interested in from a snow science point of view. So snow pillows are really just these sort of flat fluid-filled bladders that are connected to instruments that measure pressure. And then because we know the area of the bladder, we combine that with the pressure, and that tells us the weight of the snowpack that is sitting on top. It's really just a fancy bathroom scale. That's all it is. So the snow pillow has the ability to determine what is called the water equivalent of the snowpack, or the snow water equivalent. And sometimes that's just called SWE. All right, so SWE is a pretty simple concept. If you think about taking a column of snow and then just melting it down, what are you left with? Well, you're going to be left with a column of water of lesser depth. Okay, and so this lesser depth is what we refer to as the snow water equivalent. Now, the ratio of SWE to the snow depth gives you density ranging from 0 to 100%. And snow density is highly variable. So skiers in Utah like to talk about how they have the best lightest snow on the planet and so on and so forth. I kind of hate to admit it, but there is some truth to that. Okay, so in those sort of dry continental climates, new snow densities can be very, very low, 5–10%, let's say. In our sort of wetter maritime climates here in the Pacific Northwest, our new snow densities are more like 20–30%. Okay, and now in addition to this, as we go through the snow season, snow density tends to increase in a fairly monotonic way as winter changes to spring. And this is due to a couple of things. Compaction, it's also due to melting. Okay, so water melts, percolates into the snowpack, and it makes it denser. Okay. Now in the late spring, when people are out skiing corn on the Pacific Northwest volcanoes, it's not uncommon to find densities that are 40–50%. Okay. So it seems like we ought to be able to just measure our way into a complete understanding of the snow and how it's distributed across our country, right? Well, it's not entirely true, because if you look at this map, in the western United States, we have about 700 locations where the snow depth and SWE are monitored continuously. And by the way, in the context of Mount St. Helens, there are 4 SNOTEL sites in very close proximity to Mount St. Helens. These SNOTEL sites are great to check out if you are wondering what the snowpack looks like in certain places. Okay, if you're planning a trip, for example. This figure shows by color, and this was just from last week, it's showing you basically how the snowpack last week compares to the average on that day last week when I captured this figure. So anything white, green, or blue is basically saying, hey, we have more snow than usual. Anything sort of orange or red, we have less snow than usual. So these SNOTEL sites give us the quantitative history of the snow depth and the SWE over the course of the water year. And this is sort of my qualitative interpretation of what's going on, okay, during a typical snow season. There's a relatively slow accumulation phase where the snow builds slowly, and then this is followed by a much more rapid ablation or melt phase of the snowpack. So when the snow starts to go, it goes in a hurry in the spring. All right. So if you're thinking about a spring skiing weekend, you don't want to put it off, because otherwise you're going to end up putting it off to next year, because it's going to disappear in a hurry. So these SNOTEL sites are great. So if they're so helpful, what's the problem? All right. What don't we know? Well, the problem is that most SNOTEL sites are at moderate elevations in areas of fairly gentle terrain. And this is most commonly due to the need for vehicular access for the purposes of installing and maintaining this instrumentation. So in between these locations, there's all kinds of high elevation, really complicated terrain. So in other words, like, most of the snow is in places where we aren't measuring it, all right, and where we don't have knowledge of it. So that's the main problem. Okay, so it's a bit of a letdown. There's so much going on out there that we are not directly observing, and this limits our ability to estimate the distribution of our snowpack and predict our annual water supply. Okay, so what now? Well, we could just call it a day, pack it in, but that would leave us with kind of only half of a lecture and probably a half-finished beer in some of your hands. So let's think a little bit further about what we might be able to do. One option is this: we turn to computing, right? We turn to computers to simulate snowpack processes in the areas where we are not directly measuring them. There's a lot good about this, right? Computers are fast, they're happy to work overtime, they don't get cold feet out in the field, so that's terrific. So this is a computer simulation of the distribution of snow on April 1st, 2019. Super impressive, right? We can see all the main mountain ranges. We can see a lot of snow up in northern Minnesota, and so on and so forth. So maybe we should just leave things to the computers, right? No, we don't want to do that. Okay, so the bottom line is that computer models themselves, you really don't want to be overly confident in their abilities. They need help, they need oversight, they need ground truthing to make sure that they are actually doing the correct thing. Okay, I guess, but before I go too much further, we should say a few words about, like, what do we mean by a model in the first place. So a computer model is just a series of equations or instructions, and all that they do is they basically take some information in and they spit some information out, right? So it's a transfer function, turns inputs into outputs. And we develop models with the goal of reproducing variables of interest to us, whether this is stream flow, snow depth, or anything else. Well, the reality is that models aren't perfect, right? And that's because the world is really complex, and there are a lot of processes that we may not fully understand, so we can't code up in a computer to get right. On top of this, our computational abilities are often limited, and we can't model at the really fine spatial resolution that we might like to. All right, so our model outputs are oftentimes going to be different than reality. All right, they're going to be different from our observations, and this leads to an error. This can actually be a good thing, though. If we have observations, we can compare those to the model outputs, understand the errors, and then seek to use those errors to guide our models back to reality. And this kind of fusion of modeling and observations is really an attempt to harness the best characteristics of each methodology. Okay, so as scientists, we have the ability to collect data. That ability has some limits. There are only so many of us out there, and it's a really big world out there. On the other hand, the greater public is vast in number, and this brings up the interesting possibility of sort of cooperation between the two groups. And this is what is called citizen science, or sometimes it's called community science. There are many different definitions of exactly what is meant by citizen science, but the general idea is a collaboration where members of the public share data and share ideas with project scientists in kind of a conversational, iterative, reciprocal way. Okay, so if citizen science is a new concept to you, I want to point you to several online sort of portals for learning about different citizen science projects. SciStarter is a good one, Zooniverse is a good one, citsci.org, very good, and then National Geographic has a huge database of citizen science projects. And you can do keyword searches at any of these websites and sort of find something that resonates with your own interests. Okay, so I hope that you will do that. So in terms of this talk, about 3 years ago, myself and several colleagues kind of connected the dots between our interests in snow science, our challenges in getting enough of the right kind of data, and the unrealized potential of citizen science. And this led to the establishment of the NASA-funded Community Snow Observations Project. Okay, so our website is shown there, all our social media handles and so on are there. At our website, you can sort of sign up for an email list for project updates and these kinds of things. So what's the idea? Well, the foundational idea of CSO is this, that people who go into the backcountry are uniquely positioned and qualified to provide valuable data. And this is because they go to the places where snow-tell sites are not. They fill the gaps, and they can sample snow in some of the highest, most complex locations, right? Now, the CSO project is looking for data from anyone out in the backcountry, skiers, snowboarders, snow machiners, snowshoers, it doesn't matter. If you are out and there's white stuff on the ground, okay, you can contribute to this project. And the CSO project is unique in that it is more than just a backyard observer type program. Other projects like COCORAS and the Co-op Observer Program have a very long history of collecting snow depth information at fixed locations like schools and people's personal backyards. Now, until fairly recently, backcountry skiing was kind of thought as sort of a fringe activity, and it was done by people wearing wool and you know, telemark skiing, okay, in leather boots. In addition to that, I will say, and Mount St. Helens is here on the left, the advent of better gear, triple-digit resort lip ticket prices, and the just constant search for new adventures has led to an incredible growth in backcountry winter recreation. So it can be getting crowded in some places on some days, but you know, if you think the backcountry's crowded, it still beats the front country in terms of getting away from your fellow humans and having a nice quiet day out in the woods. Now, when it comes to the backcountry, we have a decent idea already of where people are going. All right, now this is a wintertime heat map from Strava, which is basically an online social network for outdoorsy types. And some of you may be able to tell right away, just looking from this heat map, where this is. Okay, so this is actually Mount Hood, and you can clearly see that sort of the main south side climbing route there on the south side of the mountain, Mount Hood Meadows and the Y-East face on the southeast, and then Cooper Spur on the northeast side of the mountain. And here's another example. Now, if you don't know where this heat map is from, I'll be a little disappointed. Okay, the sharp edge at the top of the image should be your clue. This is where skiers gather on the rim of Mount St. Helens to have lunch before they head back down the mountain. So the bottom line is that a lot of potential citizen scientists are out there in the wintertime. And one of CSO's sort of ongoing goals is to sign them up. So how do you succeed at citizen science? You know, how do you convince people that they should take a little bit of time, valuable time out of their day to contribute to a project? Well, we sort of thought of kind of 3 guiding principles. And first, you know, participants shouldn't need like new expensive equipment to go out and do something. All right, if you're asking people to help out and then telling them they have to go spend money to do it, they're not going to be as interested. And in addition, you don't want to have to, you don't want them to have to carry sort of heavy, complicated things. So it should be something that they've already got with them. Second, participation should be fast. It should be easy. All right, backcountry users might be out early trying to get first tracks and fresh powder, and our project doesn't want to slow people down from getting to their objectives. And then finally, the process of data submission should be something really automated and flawless. All right. Otherwise, if it's complicated to submit the data, it will just get sort of stuck with a user and never actually sent in to the project. Okay, so those are our 3 things to think about. Now, in terms of how to measure snow depth, well, this is one example of how not to measure snow depth. Okay, so potential for injury aside here, all that this approach tells us is that the snow depth is greater than some value, and that's not what we want. We want an actual value. Okay, so let's talk again about ways to measure snow depth. Okay, if you're in the front country, you probably have a number of options at your disposal. A tape measure is all you need. You can tape it to a ski pole. In this example, this is what my daughters are doing. Or you can just use a long stick or a meter stick. Okay, so there's a lot of ways of doing this. Let's see if I can get this to. Here we go. To talk about sort of snow depth measurement in the backcountry, I want to first talk about backcountry safety a little bit. Okay, so avalanches are a very real thing, both out of bounds and increasingly inbounds. Over the past 10 years, the US has averaged, I think, about 25 fatalities per year. Now, this slide is on Ruapehu on the North Island, New Zealand. And this is a slide that was set intentionally by Ski Patrol. And it really illustrates kind of the enormous power and speed of these large-scale avalanches. This is not some nice powdery cascade of snow. This is essentially like cement, all right? Slab avalanches are very dense, they're very violent, and avalanche victims often die from trauma rather than asphyxiation. So in the backcountry, it's worth your while to arrive well prepared. Now, part of this is basic training and education. And this is training is on sort of where and where not, and also when and when not to travel. Users need to sort of learn to read the terrain, the snowpack. They need to sort of understand group dynamics and decision making in order to stay safe. Now, in addition to proper education, backcountry users need to have basic safety kit with them. And part of that is an avalanche beacon, which is just a transceiver. Okay. Now, the beacon of a buried person is oftentimes the only hope of finding that person. So when a buried person has been located as accurately as possible with a beacon search, all right, the next thing to think about is like, well, we should break out our shovels and start digging to try and extract that person. Not quite. Okay, so remember, avalanche snow is very heavy. The victim may be a meter or deeper below the surface, and backcountry shovels are not that big. Okay, they have modest-sized blades. So before digging, avalanche probes are used to pinpoint the location of a victim. Okay, so what does this have to do with citizen science? Well, if you own one or if you've seen an avalanche probe, it's really just a pretty sturdy-looking tent pole. It's got a sharp tip on it, and it has centimeter markings on it, right? And most of them are 2.5 to 3.5 meters long. So this is the perfect device for making measurements of snow depth, even in deep Pacific Northwest snowpacks. So we have a tool on hand for measuring snow depth. Now the next requirement is some way to record that information. And not only do we need to know the snow depth, we need to know the time of the location and a precise location. The time of the measurement and a precise location of that measurement. So one great option is a handheld GPS unit in a field notebook. Okay, now the main upside to this is reliability. All right, pens and paper don't run out of batteries. Dedicated GPS units have great battery lives as well. The downside is it takes some time. Pulling out your notebook and writing down all this information takes a bit of time. And then later, you're asking somebody to manually transcribe their information into a computer and upload it. Okay, so that's going to be a barrier to getting people involved. A potentially better tool is pretty much probably in everybody's pocket right now, okay, or bag, whatever. The reality is that the typical smartphone is an unbelievable tool for research and science. It helps to enable citizen science. It has a quite accurate GPS in it, and it's connected to cell service or the web. So you can submit data very, very easily. Now, remember we had 3 requirements: no new equipment, fast and easy. Okay, we got that with the probe and the phone. Automation, okay? We need participation to be easy so that people follow through and that the data is automatically sent to the project. So we want the actual data submission process to be fast, to not have errors, and we have 2 ways of doing this. We have 2 platforms that we have essentially developed and developed collaborations with. The first, Mountain Hub. Okay, so Mountain Hub was founded in 2015 with this vision of crowdsourced information network for the outdoors. Mountain Hub was acquired by the outdoor company Mammut in 2017, and then we actually took it over just this year. So we have a new version of the app coming out and a lot of changes to it. The second platform is called Snowpilot, and this is a desktop application. And this is something that's used primarily by snow professionals, ski patrollers, avalanche forecasters, those kinds of people. All right, so we have two ways of getting information to our project. And we have all kinds of tutorials on how to do this on our website. And also at our YouTube channel, we've created some sort of nice, easy to follow video tutorials of how to do this, how to pick a good site for collecting data, how to do it on your phone, and all these kinds of things. So with a minimum of practice, it only takes a few minutes to stop, pull out your phone, make a measurement, enter it into your phone, and then carry on. And you don't need to be in cell service. Even if you are out of cell service, your phone's GPS still knows where you are. So it will store that data and it will upload it later when you get back to Wi-Fi or a cell signal. Okay, well, has it worked? Well, since 2017, we've received about 15,000 measurements from close to 3,000 unique participants. The project has been dominated by submissions from North America, so USA and Canada are our primary data providers, but we are starting to make significant inroads in other parts of the globe as well. Okay, so what do we do with this data? Well, first of all, we give it away. Okay, so all of this data is online, and we have on our website, if you go to the Snow Data tab, we have a variety of ways that you can look at, access, and explore all of the data that's been contributed to the project. So you can investigate a region of interest, and you can look at analytics in that area, how many submissions, their average values, changes over time, and then you can download all of the data as just a simple text file. So our project is open data, it's open source, we have GitHub website, GitHub repositories with all of our codes and things like that. So I invite anybody who's interested to go ahead and access some of those tools. So to return to the original goal of the project, right, we use this data that comes from our citizen scientists to improve our computer models of the distribution and evolution of snow in high mountain environments. That's our vision. Now, remember this flow chart, right, for how a computer model actually estimates some variable of interest, and how this estimation may be an error when it's compared to an observation of that variable. So if we include these observations that we now get from our citizen scientists, and we use them to steer the simulation back to reality, that is what is called data assimilation. So this is what we're doing with these data. So we first tested this concept at Thompson Pass, Alaska. Now, Thompson Pass is a very important road corridor. It's the only road that connects Valdez to the rest of Alaska. And there's a whole bunch of avalanche paths that cross it. You're seeing a large slide here on the left. Thompson Pass is also a brilliant place for winter recreation, snow machining, boarding, skiing, a lot of heli guiding operations up that way. Okay. So we developed a Snowpack model that included Thompson Pass. It also included one SNOTEL site, and then it included a large number of CSO observations. So we built the best possible Snowpack model that we could, calibrated to the SNOTEL site. And then we set out to sort of test the effect of backcountry user participation. So before getting into the results, though, let me just say a few words about how do we know if a computer model is working well, because I want everyone to understand what I'm going to show you here results-wise. So remember that the model is trying to reproduce the real world. So if we plot modeled versus observed values of some variable, you want them to fall on a 1-to-1 or a 45-degree line. Okay, that's the line of perfect agreement. So let's look at a couple of examples. So in this first case, we see that our model values are kind of increasing as the observed values increase. Well, that's good. That positive correlation is a good thing. But what's not so good here, though, is that the modeled values are consistently high. So the model is biased, okay? So that means that we basically have a problem with our computer model. Now, in this second case, what we have is basically data that seem to straddle that 1-to-1 line, Okay, so the bias seems to be gone. Sometimes the model is too high, sometimes the model is too low, but now we have a lot of spread in the data. So our data cloud is pretty wide. So we have kind of a weak correlation in this case between the model and the observations. So that's also not great. So what we are really hoping for is something that looks like this, okay? In this case, we basically have very little bias, and we also have quite strong correlation between the observations and the model values. Okay, so this is what we're looking for in terms of judging the success of our Snowpack model. Okay, so how do we do? Well, on the left-hand side here, again, we're looking at modeled snow water equivalent versus observed. And on the left is our best case. This is the best that we could do without citizen scientist participation. At the beginning of the water year, the model is correctly building snowpack, just like the observations, but the model has a large positive bias and it's building too much snow. Later in the season, the model is still showing SWE even when the SNOTEL site says, nope, there's no snow there at all. Okay. Now the reason for this was traced to the weather product that was used to force the model. It was simply too wet, and the calibration of the model could not overcome this. This is not uncommon in mountainous areas, especially so in the coastal mountains of Alaska, where weather models really struggle with the complex terrain. So if we repeat our model runs with the same weather data, but now we include the occasional correction that comes in from a citizen scientist observation, we get the figure on the right. Now, in this case, the vast majority of the data points are right on that one-to-one line, both for the accumulation and the ablation phases of the snowpack. So this is an outstanding success. And to make clear, this was completely grassroots. We did not tell people where to sample. We didn't tell people when to sample. We just said, hey, people, if you're out in the snow, can you collect some data and send it our way? And this is what we get. Okay, so we let users choose how and when they want to participate, and that seems to be a good strategy. So we have expanded our modeling network beyond Alaska, and so we currently have models running in 6 different Western states. In each of these states, we are asking snow enthusiasts to join our project by picking up the Mountain Hub app and sending in some snow depth values from time to time during the season. All right, we sort of bring our modeling work wherever we see the public respond. And that's been the reason why these particular areas have been chosen so far. So why should you take a bit of time to submit snow depth data? Well, we are able to provide high resolution and high accuracy information on snow distribution and evolution back to our participants and anyone else who wants it. So if you enjoy having information on snow available to look at as you plan your winter, consider being a part of the production of that information. We can also return to participants information about how the snowpack in a given year compares to past history. So we pre-compute statistics of snow depth at all locations and all days of the year. So when we get a measurement like this red dot here that came in mid-February on a particular year, we can show the user what does the snowpack typically look like at that location on that day and on other days of the year. So we frequently hear from participants that their understanding of snow and how snow is distributed and changes has improved as part of their participation in CSO. Our project is also partnering with other NASA projects that aim to develop better airborne and satellite technologies for measuring snow water equivalent. By measuring snow on the ground, CSO participants will directly help the SnowX team by validating their airborne measurements of snow properties. And these airborne measurements, these airborne campaigns will directly influence the development of future NASA snow satellite missions. So like sticking an avalanche probe into the snow to record depth doesn't feel like rocket science, but it actually is in the end, which is pretty cool. And snow melt may flow downhill in the spring, but small efforts from citizen scientists flow uphill, and they increase our global understanding of snowpack and its role in our water resources. So as I start to wrap up here, I'd like to point out that CSO is a huge team effort. We have a great crew of snow and data scientists who lead this effort, and an amazing group of regional ambassadors. These ambassadors are mountain guides, they're professional athletes, they're snow scientists, they're teachers, and they're just backcountry enthusiasts. So they all help to sort of support, advertise, and improve the project in their own and different ways. And they also help to educate the public about the project and about snow and water science. Finally, I'd like to thank the members of the public, okay, who have joined this citizen science effort so far. Remember, all you need is your phone, Mountain Hub app, and a measuring device, and a few minutes of your time, and you're good to go. So there is no crowdsourcing without a crowd, and we really look forward to welcoming many new citizen scientists this coming snow season. So thanks so much for sharing your evening with me. I'd be happy to answer any questions that have come up.
Thanks so much, David. That was great. One question that we got in the chat was, is there a simple way to measure SWE? And for some, can you remind people what SWE stands for?
Yeah, so SWE is, hold on, is snow water equivalent. And, you know, if you're in an area where there's not a whole lot of snow, you can do it yourself. You can just sort of get like a piece of PVC from the hardware store. And it's the kind of thing that you can sort of go out into the snowpack and sort of push it down into the snow and then withdraw it. And it's going to give you a depth of snow. And then you could just drop that snow into a pot and melt it on the stove. And that will give you the water equivalent. The more complicated, expensive way of doing it is with the type of device that I showed in one of my slides earlier. And this is a snow coring device, which has cutting teeth that are pretty sharp right there. And then these come in 1 meter increments. So you can screw these, several of these together. And you go out into the field and plunge this into the snow and withdraw it. So measuring snow water equivalent, essentially you need to be able to measure the depth of the snow and then the volume of the snow, the volume of the water that's in there.
That's awesome. Thanks so much. And I'm glad that there was a prop involved. That was very exciting. Of course, I think the biggest question that people might have is, how can they get involved? How can they get involved with CSO or any other projects that are happening?
Yeah, well, the best way to get involved with CSO is to just visit our website. And at the bottom of our website, there's all the links to our sort of social media channels. We use them for different purposes. We try and push out information frequently that's of interest to people based on snow, based on water, based on lots of different things. On our website, we have a blog, and we get a lot of guest blog entries from other snow citizen science and other water citizen science projects. So it's a real community, you know. Ours is one of 3 or 4 snow citizen science projects that are out there, and they're all neat. They're all doing different things. And so whether it's getting involved with this project or another one, it's just a great thing to do.
And one person on the chat is wondering, you know, how do you know where the bottom is? It seems like some of the snow depth might be so deep that a backcountry user might not be able to have a long enough pole.
Yep.
Or an avalanche probe doesn't reach all the way to the bottom. So how do you actually know where the bottom is? That's
a great question. And so, like, and again, we in some of our tutorials, we try and give a little bit of information on how to do a proper measurement. You know, when you go out and stick a probe into the ground over and over again, you sort of develop a feel for it. And, you know, your probe will go down and give a little bit, and you'll pull it out and you'll see a little bit of dirt on the tip. That's a great indication. And it just gives a little bit. It feels very different from hitting a rock, for example. So if you probe and you hit something really, really hard like that, you might want to move over and probe a few feet away to see if you're consistently getting the same depth. And you can tell that you're hitting the ground. Avalanche probes are very sharp. So even if there's like a really hard crust, like midway through the snowpack, you're going to be able to get that probe down through it. Exceptions to that would be like an ice surface. So it is possible that you might, like if you're measuring seasonal snow on a glacier, you're going to get down through that snowpack and you're going to hit something really hard, and that's the glacier surface itself. In terms of depth, I will say there's only one time that I get this question from people up near Mount Baker a lot. They're like, our snow is 5 meters deep. And there is a point where an avalanche probe isn't going to do it. If you are just beyond the depth of your probe, like sometimes what you can do is you can actually dig a shallow pit. So I've done that before, where I've probed to the end of my probe and I've pulled it out and I've dug like a half-meter pit. And then I've probed into that pit and I've been able to get the ground surface. So if you're a little creative, you can come up with ways. Yeah.
Someone else is asking, how do you translate those depth measurements to the snow water equivalent?
Right. So there's different ways of doing that. We actually, as part of, well, most Snowpack models have equations in them that basically sort of model simultaneously the density and the depth. So we could assimilate into our models either measurements of SWE or measurements of depth. So what we choose to do is we take the depth measurements from the citizen scientists that participate, and then we have developed a really nice sort of regression model that will translate that depth into a SWE value. And we put a paper out on that in the cryosphere last year, and it works really well. All it takes is basically, you know, your physical location, your latitude, your longitude. It takes information about what day of the year is it, and then the depth measurement, and it turns it into a SWE value. So yeah, if people find my website, they can find that paper and see more of the details about how we do that.
And of course, we all know that climate change is really affecting our snowpack year to year, like you mentioned during your presentation, that some years, you know, there's great fluxes. But I'm wondering sort of what's your outlook on how climate change is going to continue to affect snow loads in the Pacific Northwest, both short-term and long-term?
Yeah, actually, can I share my screen back for a sec?
Of course.
Let's see if I can share the right one this time. Okay, we're back to that. Yeah, so I did put a couple of slides in here because it is kind of a common question. Oops, hold on. So let's see here. Here you go. Let me show you guys this. So these are some figures that I prepared last summer, I think it was. We basically went and we analyzed all of the snow tell sites in the western US. All right, there's 700 or so of them. They all have periods of record that are 30 to 40 years or so. So we analyzed basically the peak SWE values for all of those snow tell sites. And then you're right, there's all this sort of year to year variability. So you have to only look at the sites where you have statistically significant trends. And so in these figures, let's just look at the one on the left. That's the April 1 SWE. In that figure there, all of the gray dots that you see are snow tell sites where there's not a statistically significant change. Any place you see kind of red or orange, these are locations that are showing statistically significant declines in snowpack. And any place you see blue, it's an increase. All right, so of the 500 or 600 or so sites, there's about 50 stations that are showing decreases in snowpack, and there's like 3 that are showing increases in snowpack. So it's pretty convincing that when you look at the whole western US and you look at these long time periods, that snow is on a steady decline. In terms of future changes in snow, this is another figure that I sort of prepared last summer. And what I did here is I basically took the locations of all of the ski areas in the United States. Okay, I forget how many hundreds it was. And I am essentially comparing here, looking long-term, so like 2070 to 2100, and looking at the most pessimistic scenario in terms of emissions. All right, so this is like the doomsday scenario. All right, so we're looking at the worst possible case. I'm comparing the future precipitation as snow that we get, and I'm comparing it to what we have now. And same deal with kind of the way that the colors work. You know, the redder it gets, the worse. All right. So you can see in the Pacific Northwest, it's not great, you know, fairly significant reductions in precipitation as snow. The Rocky Mountain states and the upper Midwest fare better because they are just much colder. So even 3, 4, 5 degrees of warming in areas like that isn't going to matter that much in terms of them still getting their winter precipitation as snow. The Northeast and then the sort of mid-Atlantic states are the ones that are definitely the sort of the most at risk, if you will. Okay.
Thanks so much for sharing that. And I mean, I'm the program manager at Mount St. Helens Institute, so I'm sort of curious where the overlap might be for getting snow data at Mount St. Helens. Obviously, any recreationists, it sounds like, can plug in via your website. Are there specific projects that are already in place for places like Mount St. Helens, or are you all just collecting data at large?
We, to this point, we have been kind of collecting data at large as a way of kind of building momentum. And then when we sort of get like a critical mass, we sort of divert our attention over that way. And so we would love to basically be able to sort of implement like one of these really high resolution snowpack models in that area, and having sort of kind of regular participation there would give us these data points that would help us to sort of make that model the best possible model that we could have. You know, the animation that I showed a few slides ago, that was from the Tetons, and that's a place where we've had a lot of participation, partly in collaboration with the Teton Science School. So a lot of times having an educational type program is a really good sort of stepping stone to sort of get people informed about the project, educated about the project, whether it's, you know, postings at trail heads that sort of inform people about it, or information on websites, those kinds of things.
Well, that's really exciting, and that definitely has my gears turning about how we can collaborate in the future. We're just about to wrap up here. I wanted to see if you had any other things that you wanted to mention to the group. Or I linked communitysnowobs.org in
That's
our
right.
chat.
Yep.
So folks can go to that link. It's in the Facebook chat if you're interested, or you can Google search Community Snow Observations to get involved, learn more about it. Any other final thoughts, David?
No, I'd like to thank people for coming again. I mean, I have a lot of appreciation for organizations like yours that are finding ways to provide good programming kind of during this year, you know, as a way of keeping people interested and engaged. And so I'm really happy to be a part of that.
Thank you so much for being here. And for all of you out there, our next Views and Brews will be at the end of January. The speaker is to be determined, but in February, on February 22nd, we are partnering with thematically the Northwest Avalanche Center for a free avalanche awareness course. So same sort of thing where we are going to live stream to our Facebook page, and you all can check it out through Northwest Avalanche Center and get a lot of great information about how to travel safely in the backcountry and build more awareness, and some of these skills that David is talking about, using the probes and that sort of backcountry travel, so that maybe you can be better equipped to be involved in community snow observations as well. We are launching our 2021 program season soon. You can visit our website, mshinstitute.org, and head over to the Explore tab to take a look at what in-person programs we are going to do next summer and springtime. And we also have our Volcano Naturalist program, which is virtual. It's coming up early next year. You can head to our website and search for the Volcano Naturalist program. It is a 12-week series. It is all online with a couple of in-person optional field trips. And we would love to see you out on the mountain, and we hope to explore the volcano with you soon. David, thank you so much. And to all of you out there, cheers and have a good night.